So today's topic is modulus of rigidity. In last lectures, we have seen some problems on the first two modulus that we have studied earlier, that is Young's modulus and bulk modulus. Okay. So first we will see what is modulus of rigidity, then we will find out its relation. Now modulus of rigidity is defined as the ratio of tangential stress to the tangential strain or a shearing strain. Okay, so we will see now what is a tangential stress and what is shearing strain. Now as you can see in the diagram, we have to consider a solid cube. Okay, that cube is having 8 sides, that is A, B, E, F and C, D, H, G. Okay, so we are considering a cube, solid cube with the sides A, B, C, D, E, F, H, G, H. The lower face of the cube, that is C, D, G, H. Okay, this is the lower face of the cube. It is fixed, and a tangential force F is applied on the upper face of the cube, which is A, B, E, F. Okay, so due to this tangential force which is applied, the upper surface A, B, E, F is displaced to the position A prime, B prime, E prime and F prime. Okay, so due to the tangential force, the upper surface is displaced to the new positions that is named as A prime, B prime, F prime and E prime. Now each horizontal layer of the cube is displaced, okay, and the displacement being proportional to its distance from the fixed plane. Okay, so the shearing strain is defined as displacement of the plane upon distance from the fixed planes. Now the displacement of the plane is what? A prime. This is the displacement of the plane. So displacement of the plane is A prime divided by distance from the fixed plane. Now this is the fixed plane, C, D, H, G is the fixed plane. So the distance of the displaced plane from the fixed plane is what? AD. So A prime upon AD is equals to shearing strain. Now if you see the diagram, this distance AD is capital L and the displacement we name as a small l. Okay, so if this will become A prime is small l, AD is capital L. Okay, so the shearing strain is small l upon capital L. Now if you see this diagram, this triangle DAA prime, okay, it is right angle triangle, and angle ADA prime is angle theta. Okay, so if you find out tan theta from that, what will be tan theta? Tan theta will be equals to opposite side upon the adjacent side, that is small l upon capital L. So the shearing strain small l upon capital L will become equals to tan theta. Now when theta is very small, okay, so the angle of displacement is very small. Theta is small, so we can write down tan theta is equals to theta. Therefore the shearing strain will become equals to theta. Okay, hence the angle through which a line originally perpendicular to the fixed plane is turned is a measure of the shearing strain. Okay, so what is shearing strain? It is the angle through which a line originally perpendicular to the fixed plane is turned. Okay, or it is by how much angle it is rotated or turned or displaced. That is called as a shearing strain. Now we have defined modulus of rigidity as tangential stress to the shearing strain. It is defined as it is denoted as eta. Okay, the modulus of rigidity is denoted as eta. We know that Young's modulus is denoted as Y, bulk modulus is denoted as capital K, and the modulus of rigidity, okay, it is denoted as eta, which is equals to tangential stress upon shearing strain. Now as per the formula, we know that stress is what? Stress is force per unit area. So tangential stress will be equals to F upon A. Okay, where A is the area of the surface A, B, E, F, which is displaced. Okay, and divided by what is shearing strain? We have defined here shearing strain is equals to theta. Okay, so eta will be equals to capital T upon theta, where capital T is the tangential force applied. Tangential force applied per unit area. Okay. Now, the units and dimensions of modulus of rigidity are those of stress or pressure. Okay, like Young's modulus, only solids possess the modulus of rigidity. Liquids and gases do not have a definite shape of their own, hence they do not possess modulus of rigidity. Hence, only solid possesses all three types of elastic constant, while the liquids and gases possess only one elastic constant, which is bulk modulus. Okay, why? Because it is dependent upon the volume change. So that's it with the third type of modulus, that is modulus of rigidity, which is defined as the ratio of tangential stress to the shearing strain. Now the next topic that we are going to see is work done by a shearing strain. Now the next topic that we are going to see is work done in shearing strain. Okay, in the we have seen earlier what is shearing strain and how it is defined. Okay, now we will see a derivation for the work done in shearing strain. Now for that we have to consider a cube. Let L be the length of each side of the cube, and a surface area of each face is equals to A equals to L square. Okay, it is same as the previous diagram. The diagram is same as previous diagram. L is the length, okay, of each side of the cube. Now it is not like the diagram does not shows that each side of the cube is same, but we have to assume that the modulus of rigidity of the material of the cube is eta. Now, the base of the cube is fixed and the tangential force F is applied to its upper face as shown in this figure. Getting it? Now this L is the length of each side of the cube, and small l is the displacement of the upper surface, okay, the points upper surface of the cube due to the tangential force F which is applied on it. Theta is the angle made by the upper surface with the fixed surface. Now it is sheared through an angle theta. Then shearing strain we have, as we have defined earlier, is equals to theta, and modulus of rigidity becomes F by A, that is force per unit area divided by theta. Now since we know that, from that we can find out force F will be equals to eta into theta into A. Okay, so therefore F is equals to eta L square theta. Why? Because L square is the area of each side of the cube. Therefore F becomes, since A is equals to L square, F becomes eta L square theta. Now from this figure as we have shown earlier as well, theta is equals to L by small l by capital L. Okay, where theta actually it is equals to tan theta, but when theta is very small, we consider tan theta is equals to theta only. So theta is equals to small l by capital L. So we'll write it down over here. There, since theta is equals to small l by capital L, so F will become eta L square small l by capital L, which is equals to eta L into small l. Okay, so this is the force F, tangential force F, which is applied. Now work done for a very small amount of shear d theta by displacing the force F through a small distance dl is given by work done is equals to F dot dl. Okay, so we know F is equals to eta into capital L into theta. We substitute it over here, so we get dw is equals to eta L small l dl. Now hence the total work done during the whole displacement from 0 to small l or during the whole shearing strain theta will be given as W is equals to, that is work done is equals to integration of 0 to L eta L small l dl, which is equals to half of eta L square. Now from the previous equation for the eta that we have seen earlier, eta is equals to F upon L square theta, Now as theta is equals to L by L, substitute it over here, so eta will become F upon L square, L upon capital L. This L and this will get cancelled, so what you will get, eta is equals to F upon L into capital L. Now from these equations, that is equation number, the above equation for the eta, which is okay, so we get work done W is equals to half of F upon L into small l into L square. So W is equals to half of F into L is equals to half of tangential force into displacement. The volume of cube is L cube, therefore work done or energy stored per unit volume is equals to half of F L upon L cube is equals to half of F by L square into L by capital L, which is equals to half of F upon A into theta, which is equals to half of shearing stress into theta is equals to shearing strain. So we see that work done per unit volume of the material in any kind of strain is equals to half of stress into strain. Okay, as we have seen earlier also, while finding out the work done due to longitudinal strain or work done due to volume strain while studying the Young's modulus and the Bulk's modulus. Okay, so that's it for today's lecture. Thank you.